Okay, let's make some announcements. The homework has been extended till Friday, so that's hopefully going to give you guys a bit extra time. So the due date now is Friday at 4 p.m. Usual place, turn into Mallory's office. Your proposal is due today. I just wanted to clarify something because I think people maybe are placing a little too much weight on the proposal, or no, it's not a proposal, the milestone 2, number 2. So the way we've graded the milestone 1 and the milestone 2 is going to be the same way is that it's mostly graded for completeness. You know, if you have a milestone 2 that's not terrific but it's good, that's not going to affect your final grade for the project very seriously. The purpose of the milestone is to get feedback. Okay, so I wouldn't spend a lot of time if I were you writing this in a way that's very eloquent, you know, having the most pretty looking figures. You're supposed to convey to us your progress, and we're supposed to be giving you feedback. That's where you should be putting most of your time into. Do you have all of the things expressed in there that you're doing, the things that you're having trouble with, the things that you need feedback on? As long as those are clearly expressed, it doesn't have to be like a polished paper at this point. We're not going to be taking off points if you don't have a very polished report. So that being said, there is a process that we're trying this year for peer review, and it's completely anonymous. So you can't see who's reviewing your milestone number 2. They can't see whose milestone number 2 you're reviewing, etc. And the scores from that peer review, they do not count towards your final grade in any way. So if your classmates all loved your milestone 2, sorry, doesn't get you kind of gets you chances to get extra points, which I'll explain in a second, but it doesn't explicitly get you extra points. And if your classmates all dumped on it, then okay, we encourage people not to do that, but that doesn't give you don't get points taken off. Okay, we're still going to grade your milestones in our own way. But what the peer reviews do is that they provide you an opportunity to get extra credit. So the top 6 scored peer-reviewed milestone number 2, we're going to pick to give longer presentations at the end of the semester during the final kind of class presentation period. So and then we're going to pick from those maybe the best one, and that person will get extra credit. Okay, so if you do well in terms of those scores, then that's all that the result is. You get to give a presentation at the end of the semester rather than a poster, say. Okay? Any questions about that? Did you have something you want to say?
Yeah, I just wanted to say for the anonymous part, I think that relies on people submitting their milestone 2 without their names on it, which is like how you would submit it for review at a conference. So I think we made that clear in the directions, but you should do that.
Yeah, thanks for clarifying that. So make sure that, so there's some directions on the course website for how to submit to this system called EasyChair. It's just an online system for collecting this stuff that is used for conferences as well. You have to submit an anonymized milestone 2, otherwise this whole process doesn't work.
The anonymous case, so our project is based on a paper which we have submitted to somewhere, but it's not still it's still not published. So what should I do in that case?
Based on a paper, so the
paper is an extension. So our project is an extension of a paper which
yeah.
is submitted to a conference, and the reviews and decision are not out of the conference.
Okay, well, I mean, so are you worried that someone's going to Google the title of this or something? Is it submitted to archive or something?
It's not submitted anywhere.
Okay, so I wouldn't worry about it. So when you go to review the milestones, don't do extensive Google research as to try to figure out who the author is. Just review the milestones. Okay, so nobody's going to, I think the chances of somebody being a reviewer for that conference and reviewing your milestone are pretty low. Yeah?
We submit to EasyChair. Do we also have to submit a hard copy or a PDF or anything?
No.
Separately? Just EasyChair?
Just EasyChair. And then we'll be able to tell who submitted what when we grade the milestones. Yeah. Okay? And instructions about reviewing shortly, but I think each person will review on the order of 3. So not very many. Any more questions? Okay. Any other questions about non-academic stuff before we continue with the lecture? I guess it's all academic. I meant non-material. Okay, so today we're going to finish the lecture that Matt started on Thursday, which was a walkthrough of various methods as they apply to these sum of norms regularization problems. And after this, we're going to get to some advanced topics, which will continue for the rest of the semester. Oh, I remember, I want to say one other thing. I just remembered. We have not graded your midterms. We'll grade them on Thursday. So I'm just going to hold off on kind of making any more statements about the midterm until then, because I just don't know much information about it. But I do recognize that everyone found it long. So don't worry. We are fully aware of that, and we'll take that into account. So more on that once I see the scores. OK. So I think Matt got up to the differencing operator, he said, the different differencing operators. But let me just walk you through what the problem form was so we can be on the same page. I think we're in another situation where this projector is out. OK, so I'll have to switch back and forth today. So these are the problem forms that we talked about last time. We called them sum of norms regularization problems because the regularization term, aside from f, the other term in the loss, is a sum of norms. And actually, each norm is composed of the linear transformation of our variable. So this was the problem form we were looking at. And we saw that it covered a few different problem types. And there's more that fit into this framework as well. We didn't kind of give an exhaustive list in this lecture. So we talked about fused lasso problems last time, which were problems where these operators D, these linear operators D, they give you differences between variables, between components of my variable beta. So a special case of this sum of norms problem is the case where this capital J is just 1. So there's only one norm in that sum. This Qj is just 1. OK, so it's really just the penalty is just D times beta for some matrix D. And that matrix D happens to be one that gives you differences between adjacent components of beta. So the idea here is that there's some prescribed ordering to the components. Like maybe they correspond to measurements across time, say. And by using the L1 norm of d beta in the criterion, we are explicitly kind of encoding in the fact that we want at the solution to have many beta i's being equal to beta i's plus 1. So there should be many values of I at which the solution looks constant. Okay, and then it can break at some point. So we saw some examples of that. Matt went through some examples and some algorithms. This is a case where now we've generalized it a bit so that instead of just being ordered along a line, they have some relationship according to a graph. So I can think about the components of beta living on a graph. And I want to encode in differences across edges of the graph. That's really just an extension of this problem. That's also called the fused lasso, but now it's over a graph. And this was an example where the graph is a 2D grid, and et cetera, et cetera. This was probably a good summary slide. We went through all of the methods applied to the fused lasso problem. And we saw that these were the things that we were able to do. We're able to do primal subgradient. We can pretty much always run the subgradient method. That's just there because it's always possible. Its iterations were very cheap, but its convergence is slow. It's just a property of the subgradient method that's persistent. Primal proximal gradient, we saw, was not really an option for us if D is the fused lasso over a graph, because this is not an easy prox to solve. Okay, this is itself, in many cases, the problem we're trying to solve. Right? If D is the fused lasso matrix over a graph, and we were using what we called the Gaussian signal approximator loss, like this one, for example, then the problem here is the prox operator. There's no difference between the prox operator and the problem. That should be hopefully clear. The problem is to minimize the L2 norm of y minus beta squared plus lambda times the L1 norm of d times beta. If you were to derive the prox operator for that problem, it's of the same form. Okay, so we haven't done anything really. That would only be helpful if the loss wasn't this kind of squared error loss. But even so, this is a hard problem to solve. We saw that basically primal proximal gradient didn't get us much. Okay, we saw dual proximal gradient. We derived the dual of our fused lasso problem, and it looked like this. You saw? It's the top problem up there. Came from a simple calculation involving some conjugates, which hopefully by now we're comfortable with. And we saw that actually dual proximal gradient is quite tractable here because it just involves projections onto this box. In fact, this is a projected gradient method because we have a constraint set. So that was very cheap iterations. Convergence is kind of medium, which is typical of proximal gradient methods. And then there's a dual interior point method that we saw, which comes from taking this L infinity constraint that we had here at the top and writing it instead as a bunch of linear constraints on ui here at the top. Ui should be between minus lambda and lambda in each component, and then basically forming, say, a log barrier for that constraint and using an interior point method. And we saw that basically the jury was out as to whether or not this is a good idea. It really depends on the structure of the Hessian. So this was the Hessian we derived. If this happened to be structured, which would be the case when, say, D was structured and the Hessian of our conjugate loss was also structured, then that could be a good idea, and the convergences would be rapid. But if it wasn't structured, then the iterations would be very expensive. So we may not want to do that. Okay, so those were all the algorithms that we applied. Let me pause to see if there are questions. Okay. I'm going to skip to basically, so Matt went through all of this, and we talked through the points that, for example, if we wanted a solution, say, of high accuracy for either of these problems, where now we've specified the loss, then it makes sense to use an interior point method in this case, because we can derive the conjugate in closed form, and the Hessian of the dual would be structured, so the interior point method would be quite fast. And because we want a solution at a high level of accuracy, it doesn't make sense to use proximal gradient on the dual, because if we used proximal gradient on the dual, then it would converge very slowly. Okay, that was something that we saw actually in the first lecture. This was the motivating example we gave. Came from this problem exactly. Because we want a solution of high accuracy, and because actually the dual problem is not very well conditioned, it's going to take us a long time with dual proximal gradient to get to a solution of high accuracy. It's going to still have kind of smoothed out parts of the image when we really want something more crisp and blocky like this. Okay, and the story was significantly more complicated when we included a predictor matrix or a regression matrix. And we saw that actually the dual was not necessarily a good idea at that point, because the Hessian lost its structure, for one. And it looked like we maybe were out of luck, but the idea there was that you can always combine methods. So this is an important point that you should carry forward in practice. You know, we learned formally that applying primal proximal gradient descent, you basically do when you know the prox operator. If you don't know the prox operator, we kind of said, well, you have to be careful. But in practice, people apply proximal gradient all the time when they don't know the prox operator. And this is an example of that. If we had an X matrix in the loss and we took the prox operator, that kind of freed ourselves of the X matrix. Okay, because it turned whatever the loss was in the primal, which involved an X matrix, into a quadratic that had an identity as its quadratic form. And so we're back to what looks like a signal approximator case for the fused lasso. That's the prox operator. And even though we can't evaluate that in closed form, we could now apply our dual interior point method to this. So that's something that when I covered proximal gradient in class, I said you have to be careful about, but it's something that people do all the time in practice. And in this case, if we solve this to high accuracy with the interior point method, which is not unreasonable because interior point methods are really quite accurate, then we should be fine. Okay, so that was the idea. So let me skip ahead just to one more example, because we have some more stuff on the group lasso to cover. So this is the last kind of fuse lasso example. And this is a case in which either dual proximal gradient or the subgradient method may be the go-to methods. So let's suppose that we want to solve something like a fuse lasso problem. But D, instead of just taking differences of neighbors on a graph, we actually take differences of averages of neighborhoods. Okay, so the idea is, switch to the doc cam quickly. So instead of just taking pairwise differences, like suppose I want to compare these two nodes, instead of just taking this difference, maybe I look at all neighborhoods. I take differences between all neighborhoods of size 5 of two nodes. So I take the difference between this neighborhood and this neighborhood. So that my differencing operator might be the one that actually sums up all the neighbors of this node and takes the difference between that and all the neighbors of this node. And on an image, that might be reasonable as well, right? If you remember an image, we think of the nodes as being pixels in the image. So by taking differences of averages, we are effectively taking differences of patches of the image, right? So I might be looking at now the difference between, say, this patch and this patch. Maybe it's this patch as well, and this patch, etc. Okay, so we're looking at maybe higher level structure than just individual differences across nodes. Okay, and there's maybe some motivation for that, because if we do this over several different sizes of neighborhoods, and this is what some people call multi-resolution methods. So it means we're trying to not only make things look very constant at a low level, but also at a high level. I want to make sure that the left half of my image and the right half of my image all look pretty homogeneous or something like that. So this would be called a multi-resolution method for image denoising. Okay, so I'm not really specifically telling you what D is, but I mean, you can just imagine that each row has minus ones and ones, say, as well, but it has many more of them because I'm taking differences across many different nodes. So averages of different nodes. So with that in mind, and without going into specific applications of that, let's think about the algorithms that we might apply in this case. So the problem is that this D can be quite dense, especially if I take these averages over large neighborhoods. Then this D gets quite dense because each row gets filled with many minus ones and ones. And so the dual interior point methods that we looked at before look much less favorable now, because if I take enough neighborhoods into consideration and I take the averages over many different neighborhoods of different size, then I'll be solving linear systems as part of the interior point method that are kind of in a dense matrix, because all of a sudden this Hessian that we wrote down, this guy here, say, we had the Gaussian loss. This is a dense matrix if D is dense or denser. So it doesn't really look very favorable anymore. The primal proximal gradient descent method is still intractable because we still don't know how to solve the prox. Okay, so it's really not, there's really still nothing there anymore. But now dual proximal gradient looks like a much better option. Okay, because dual proximal gradient just requires multiplication by D. It doesn't require solving any linear systems in D. And the prox operator is still very cheap. The prox operator is still just projection onto a box. So it's not really any more expensive than it was before. The difference is that we're multiplying by a dense matrix now rather than a sparse one, which is more expensive, but it's not the same transition as a sparse matrix solve to a dense matrix solve. Okay, we're still kind of, relatively speaking, better off multiplying by a dense matrix than solving a linear system in a dense matrix. So especially if we didn't really want a solution of very high accuracy, this is definitely the way to go. Okay, doing dual proximal gradient. Right. This last slide is something that we haven't really talked about very much in class, but this is a problem where we have to do something that has limited memory because the problem we're envisioning is very large. And it's just important to kind of see the full spectrum of uses. And this is a case where maybe the primal subgradient method might be the best idea, even though we've routinely dumped on it for this lecture on case studies because it seems like it's very slow. This might be our only option at this point, and it actually may not be a very bad idea. So let's go back to, let's just go back to the problem real quick so I can write down you can remember what the subgradients are. So the problem was of this form, let's say. And the primal subgradient method, if we just applied subgradient method to this problem, we'd have to take subgradients of this criterion. And that looks like this. Let's call it gamma, say. So I use the chain rule here for subgradients. Right here I'm taking the subgradient of the L1 norm composed with a linear function. And it's that linear function transpose gamma, where gamma, you might write it like this. It's a subgradient of the L1 norm evaluated at d beta. Okay, I just mean that I just take a regular subgradient of the L1 norm and I evaluate it at d beta. That's the subgradient of this loss. These are the subgradients of this loss. And okay, let's just write out what this is. This is actually equal to, I can think about this as the sum of di, or let's call it dj gamma j, where dj's are the rows of d, and gamma j are the components of gamma. Here I'm just writing this as a linear combination of the columns of d transpose, which are the same as the rows of d. Okay, so this is just another way of writing this matrix vector product. So that's my subgradient. And remember what gamma j is. Gamma j is equal to, it has to be equal to either -1 or 1. Right? It's equal to -1 or it's equal to 1 if, let's say, the corresponding entry of d beta is either strictly less than 0 or strictly bigger than 0, because that's the definition of the subgradient of the 1 norm. Otherwise, it's anything in between -1 and 1. So what is a valid choice of subgradient? A valid choice of subgradient is just to take these gamma j's to be 0 whenever the corresponding jth component of d beta is 0. We're going to do that because actually that makes the sum have far fewer terms. That's the point. So a valid choice of subgradient is just this one. And I'll write this sum j and s, where s is equal to the set of all j's, such that d beta is not equal to 0 in the jth component. And in that case, actually, these are just 1s or minus 1s, right? So they're quite simple anyways. So why is this a nice representation? It's because if D was huge, if D had many, many, many rows, like, for example, in this dense differencing operator, each row of D represents a difference between two different groups. If we looked at differences between groups of neighbors of sizes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's a lot of rows in that matrix, right, for an image. Because there's a combinatorial number of rows for each of those neighborhood sizes. So that I'm going to have a matrix with a lot of rows. By representing the subgradient like this, I'm only actually required to sum up the dj's times these gamma j's over a subset of the rows, and only rows for which the differences are non-zero. So if I have a very sparse problem, then I can get away with basically forming a subgradient very cheaply. I have a very sparse problem in the sense that I had a big enough value of lambda that I've chosen so that many of the differences that I'm seeking are 0. Then the subgradient can be much cheaper to form than a full multiplication by d transpose originally, right? Because basically the point is that a lot of the entries of this gamma are 0, or can be taken to be 0. So in that case, if we had a very, very big matrix, D, because we had a large image, or so let's say an MRI, which was a 3D version of the images that we were considering, like a 3D grid, and I was taking a dense differencing operator over many different sizes of neighborhoods, then D itself could be huge, very, very big matrix, maybe so big that I don't want to even put it in memory. And by recognizing that subgradient can be written like this, I can actually get away with pretty cheap updates according to the subgradient method. And for a big enough problem, this may be my only option, or really the best option. So this combined with perhaps a stochastic trick, meaning one that picks a subset of S over which to evaluate the subgradient, not the full S, but a random subset of S. Or maybe if F was a sum of functions, picked a subset of those functions over which to evaluate the gradient. That would be the stochastic way of representing these two. Probably a stochastic trick combined with this realization could be something that's quite effective at large scale. And at that point, that might be the only thing that we can do. Questions about that? Yeah, Han. I didn't really understand, sorry.
So how to solve the equation here to get the max beta?
How to get the next beta?
Yeah, in each iteration.
I mean, it's just a subgradient step, a usual subgradient step. So I add this to, right, the subgradient. Are you not seeing my hands? You're not. So it's just a usual subgradient step, right? Beta plus is beta minus, t times the subgradient. We'll call it g.
You mean you are using the subgradient, not a proximal?
Yeah, I wasn't talking about proximal methods here. Yeah. Okay. So let's switch gears a bit and talk about a different class of problems. And we're going to see that actually different methods now are going to work well now that we've changed the norms. And interior point methods in particular are going to be not nearly as tractable in general, even though they were quite effective, it seemed, for the fused lasso problems. So we're going to talk about group lasso problems and then something called group fused lasso problems, both of which fit into this framework. So the group lasso, which we've talked about I think a few times. Once there was one thing on your homework about that. We may have mentioned it as well in class. And I think you had a question on the midterm about group lasso as well. The group lasso is, it's a problem which you're seeking sparsely, not over individual predictors, but over groups of predictors. So it's like a version of the lasso where instead of trying to set components to 0, I'm trying to set entire groups of coefficients to 0. And the idea is that maybe I have some pre-specified group structure in my predictor matrix X. So remember, X are my variables. The columns of X represent different variables, say in a regression. Let's suppose like a linear regression you can think of even. And I've grouped them. And I'm going to label the groups 1 through J, capital J. I guess I put a G here. Maybe you could just think of that J as a capital G. And to achieve sparsity over groups of predictors, rather than individual predictors, I'm going to think about splitting up the coefficients, beta, into the corresponding subblocks. So if X1, the first group, was over columns 1 through 10, then I'm also going to write beta 1 to be the first 10 components of beta. And if X2 was then, columns 11 through 20, then beta 2 is components 11 through 20 of beta as well. So I basically make the analogous division of my coefficient vector beta, and I can solve the following group lasso problem, where, again, you can think of this maybe as like a linear regression of y on some variables x, or a logistic regression or something else. That's what the first term is. The second term is what gives me sparsity in a group sense. So here we're using the L2 norm on subblocks of my coefficient vector beta. And we're summing them up with weights in front. Okay, so these WJs are just, you can think of them as constants with respect to the optimization problem. So this fits into the framework we talked about, just because each of these choices of norms now is just the L2 norm. And DJ is just a matrix that just gives you, if you write DJ times beta, has to give you just beta J. So it's the matrix that just selects out that particular group. So the group lasso is an interesting problem. It was proposed after the lasso, about 10 years after the lasso, and it has many other names, just like the lasso goes by other names. And another choice of norm than the 2 norm to give you group sparsity is the infinity norm. I think maybe the infinity norm is a little bit clearer as to why that achieves sparsity across groups. The 2 norm is maybe not intuitive, but you can see why it achieves sparsity across groups from the KKT conditions. I think that itself was actually one of the problems in the midterm. So if we were to take the KKT conditions here, we would see that actually the solution is going to satisfy the property that either an entire group is going to be 0 at the solution, or it's going to be generically non-zero. The infinity norm will achieve the same thing. It just does it somewhat in a different way. Right? If I'm penalizing the maximum entry across all components of a group, then you can see that to make that 0, I have to set them all to 0. And once I allow that to be non-zero, then there's no penalty on making all components of the group non-zero. Right? So that's the intuition behind the infinity norm. So a nice example of the group lasso is something called sparse additive models, which was developed here at CMU. And the idea is, let's suppose that I want to model some points y as a non-parametric function of some input data. So if the word non-parametric doesn't make sense to you, you can forget about that. I just want to model y as a nonlinear function of some data. So I have pairs zi, yi, where zi is a d-dimensional predictor or covariate, and y is just some continuous response. And I want to model y as a nonlinear function of z, rather than a linear one, which is what we've mostly talked about for the optimization problem so far this semester. And the idea is that I'm going to actually model y to be a sum of functions in each dimension. So pictorially, it's like saying that if I just had d, if d was just 2, then I'm going to basically model the relationship between y and z1, which is the first dimension, according to some nonlinear function. I'm going to model the relationship between y and z2 according to some other nonlinear function. And then to get y as a function of z1 and z2 at any point, I'm just going to add up those 2 functions. So I'm going to pretend like the function of interest decomposes with respect to the coordinate axes. And this is something that people like to do, because if d was very large, then you've simplified your estimation problem considerably. You're just thinking about really d almost one-dimensional functions to fit. It's called an additive model. So a sparse additive model, if that's an additive model, a sparse additive model is one in which we actually are going to declare that certain dimensions don't contribute at all. So if we have 1,000 dimensions, then maybe we only want to pick out a small number of those, like 10, over which to make essentially one-dimensional fits. And then we'd be adding those together to get the final prediction. And we'd be declaring the other 990 dimensions as irrelevant. That's a sparse additive model. So we can actually solve that with the group. We can solve such a problem in this framework, the group lasso framework, as follows. I'm going to construct a matrix X for each group J, and each group J here is defined by a dimension. So think about modeling Y with respect to dimension 1. I'm going to construct a matrix X1 that contains a bunch of candidate functions that when I add them up are going to give me some smooth fit. So I can, for example, I can put polynomials there. I can put sines and cosines. You can put down a Fourier basis. You can put down a spline basis. Just some smooth functions with respect to only that one variable. And if I were to multiply such a matrix X by coefficients beta, so x1 times beta 1, then I'm actually determining a linear combination of those functions to model just the first component for the first dimension. And I do so for every dimension. So every dimension has its own set of basis functions. Every set of basis functions has their own corresponding coefficients. And by forming the product x times beta, this is actually, if I've stacked those groups of basis functions in the columns of x, this is actually just adding up functions, some smooth functions across dimensions. That's exactly what it's doing. So now I've declared that y should be a sum of functions across dimensions given by these coefficients. And by placing now the group lasso penalty on betas, I'm actually going to be setting the coefficients for a bunch of the dimensions to be all 0 exactly. So that's going to be basically declaring that some dimensions don't contribute at all to the prediction of y, right, to the fitting of y. So that's a nice example of the group lasso problem. And here is here's just an example from the SPAM paper. I guess the acronym is SPAM for this method. And you can see that here I have some data across 6 dimensions, and I've solved this optimization problem with a particular value of lambda, and I fit a smooth function essentially to the first 4 components. But the function is identically 0 for the last 2. It's determined that the last 2 components shouldn't contribute at all to the prediction of y. OK, so the purpose of this lecture and the previous one, by the way, were just to expose you to some interesting problems that had a particular form and then talk about the optimization counterparts. If this was too fast or didn't make sense to you, then don't worry. You're not going to be tested on this in any way. I just wanted to convey to you an interesting application. It's the same with all of the examples we've talked about really so far. They're just supposed to be interesting motivation for the actual optimization routines we're running. So what algorithms can we apply to the group lasso? So let's consider either the L2 or L infinity penalties on groups, and let's walk through our tool set just like Matt did for the fuse lasso. So the primal subgradient method is it's easy to apply. Okay, all we need to do is be able to take subgradients of, so a gradient of, say, our loss function and subgradients of beta. And that we should be able to do because, so I have the L2 norm of beta, let's say, because we can recognize this. Remember, we had a rule for subgradients of norms. They were given by, if we had a norm, if I had, say, a p norm, we recognize this as the, according to its dual norm, as the set of, as the maximum of y transpose x among all vectors y that have q norm less than or equal to 1, where 1 over p plus 1 over q is 1. So from what we know about subgradients of maximums, we actually had written this down in a few places. The subgradient then is just the argmax of this expression. So it is the y that makes this as big as possible, subject to having q norm smaller than 1. So for the 2 norm, away from 0, this is just going to be x over its 2 norm. Right? Because this is the unique vector that makes this as large as possible. This is a unique vector y that makes this as large as possible, subject to having 2 norm less than or equal to 1, because the 2 norm is self-dual. Okay, and otherwise it's just, if it's equal to 0, it's just anything within the 2 norm ball of radius 1. So those would just be the subgradients of the 2 norm. Okay, so those are easy to form. We just either scale the vector down, or we just take a random direction that has 2 norm less than or equal to 1, or we could even take 0 if x happened to be 0. And for the infinity norm, it's also quite straightforward. I would just invite you to try deriving that as well. You can see that it has an expression in terms of the 1 norm. So primal subgradient is easy. It's just slow. And we might come up with an example where if the problem was truly huge, then it may be a good option. But for most of the problems we'll be considering, it's just too slow for our purposes. OK, how about primal proximal gradient? It's actually pretty appealing in this case. The gradient of the smooth part is easy. Just from the chain rule, it's just x transpose the gradient of h of x beta. And the prox operator is actually computable in closed form. So this is a different, now we're in a different kind of situation than we were with the fuse lasso, where the primal proximal gradient method looked like a bad idea. This actually looks like a very appealing idea. Okay, it's because notice that the linear transformation here didn't really complicate the matters very much at all, because the linear transformation that we apply within the norm just sucked out a group. It wasn't giving us differences between groups or differences between variables. And the prox operator for either of these is actually computable in closed form. And one thing to do is first just to notice that I can actually split this up for every group separately. So this I can split up into a sum over the first group of beta minus the first group of z, that L2 norm squared, the second group of beta minus the second group of z, that L2 norm squared, etc. That's just because this is just a sum over all components, so I can certainly group it however I want. And then I can realize that in either case, the prox operators decompose into j different prox operations per group. So now I don't have to worry about a sum of norms, just a single norm. So I can split it up ahead of time. And this one I claim is actually, well, you do this one in the homework, actually. This one you get by scaling z by a certain amount. And if the result is negative, if the result basically pushes you through 0, if the scaling factor you're trying to scale it by is negative, then you just set it equal to 0. Otherwise, you scale it by that amount. This one I claim, if you were to, again, get rid of the groups and just consider it on each group, this is like the complement of soft thresholding. That you can kind of guess because this is an infinity norm, and its dual is the 1 norm. So if you were to work out, say you write down the KKT conditions for this, or the subgradient equations for this, then you could see that actually this is very related to soft thresholding. It's actually like, I think it's just z minus its soft thresholded version, something like that. So both of these are very practical. You can compute them in closed form in order n operations. And they're variants of group-wise shrinkage. So they are doing something here like taking z and then shrinking among groups rather than over individual coordinates like the L1 norm would do. Let's just go through the last option, and then we'll take a break. Primal interior point methods would be something we can think about. Let's reparameterize the problem so we can apply a primal interior point method, so we can apply an interior point method directly. We didn't do this for the fuse lasso because the dual was tractable, but here the dual is not so tractable because of the X matrix, or not as tractable because of this X matrix that appears in the criterion. So we're going to just reparameterize the primal to see if we can apply an interior point method. And so here I've assumed that the norm actually is an L infinity norm on the groups. Okay, so it's this problem, but with the 2 norm replaced by an infinity norm. And I've reparameterized it by introducing a variable zj for every group. Zj is just a scalar, single value. And I've written in a constraint that beta j has to be in between minus cj and zj for every group. So that's equivalent to having the infinity norm penalty on beta j. You should hopefully be able to convince yourself that's true at this point. It's because zj here is acting as an upper bound on the absolute value of beta j in every component. Right? That's what this constraint means. And at the solution, that's going to have to be tight. Because if that wasn't tight, then we could just reduce zj to be whatever the absolute value of beta j was, the maximum absolute value. And that would make the criterion smaller. So this is equivalent to the original L infinity penalized problem, the group lasso problem. And now I can write down a barrier smoothed criterion because this is a simple constraint to deal with. And it just involves, right, 2 terms, one for this inequality and one for this inequality. So I'm writing down 2 log terms, one for each inequality. And because beta j is a vector, this is actually a bunch of linear inequalities. So these are the extra terms that I have to add to my criterion in order to get the barrier problem. Okay, so that's the setup for interior point methods for the L infinity version of the group lasso. We have an extra variable now at z. So the important consideration, which is always the case when we're applying interior point methods, is what is the structure of the Hessian? That kind of makes it or breaks it, right? The Hessian structured, we're in luck, meaning we can solve a linear system quickly in it. If it's not structured, then it seems like it's going to be very expensive to run. So we have to consider kind of 2 terms. The first is this term. This is the added terms. What is the second derivative of these? And the first term, what is the second derivative of the existing terms in the criterion? Let's talk about the log barrier terms first. It's not hard to see that this is going to be block diagonal. The second derivative matrix of these log barrier terms is going to be block diagonal. That's because if I were to take let's suppose I were to take a derivative here with respect to zj, and then I would take a derivative with respect to zl, or let's call it, sorry, zk, for some other group k, then I'm going to get 0. Because once I take a derivative with respect to zj, right, there are no appearances anymore of zk for any other group k. And similarly, if I were to take a derivative with respect to one component of one group of variables in beta, and then with respect to another component in a different group of variables of beta, that's also going to be 0. Because once I take one derivative, the only terms that appear are the terms in that group. So that means it's going to be block diagonal. And this is going to be very sparse, the Hessian of this matrix. The Hessian matrix of this term is going to be very sparse. So the other terms we have to consider are the 2 terms in the loss. Okay, and we have to take basically a derivative with respect to beta and z, because those are our 2 variables. Well, if we take a derivative with respect to z twice, we get 0, because this is a linear term. If we take a derivative with respect to beta first and then z, we also get 0. So there are no cross terms in the Hessian for beta and z. There's no pure quadratic, or no pure second derivative in z. So the only thing that really matters is the 2 derivatives in beta. And just from the chain rule, that's going to be x transpose the Hessian matrix of h evaluated at x beta times x. So this looks OK. This Hessian looks OK. We're going to be adding this to a block diagonal matrix in order to get the final Hessian. And then we're going to try to solve a linear system in that. First of all, one thing to note is that this actually is substantially more complicated than a primal proximal gradient method, right? Basically, we had to either figure out what this was, and once we did that, we could apply a primal proximal gradient. To apply an interior point method, we're already at the point where we're trying to solve a linear system, a block linear system in this plus the barrier term phi, it's Hessian, which is just substantially more complicated. So that's something we should be aware of, that we've kind of invested a lot more just to implement this method. And even so, it could actually be pretty inefficient if X was dense. Because if X is a dense matrix, then we'd have to solve a full linear system in X transpose something times X. And that's going to cost on the order of, if X transpose X was a P by P matrix, then that's going to cost on the order of P cubed operation, flops for that. Okay, so it would probably only work well if X was banded or really sparse or something. And even in that case, it would be a substantial investment to implement the interior point method, whereas the proximal gradient method would be kind of quite straightforward. So this is different from what we saw for the fused lasso, just to reiterate. For the fused lasso, the interior point method was actually pretty simple. We didn't have to introduce auxiliary variables. We did it on the dual rather than the primal. And it was kind of always structured by nature just because of the D matrix. And primal proximal gradient was not very efficient. It's almost the opposite here. Okay, primal proximal gradient looks much better, and the interior point methods look much more complicated. So that was our walkthrough for the group lasso. Let's take a break, and then I'll come back and do some examples.